Every model so far trains something: weights, splits, margins. This one trains nothing. Zero. Not a single parameter.
So how does it predict anything at all?
It just looks at the nearest points around it and copies them. Change one number and accuracy can swing by 20 points on the exact same data.
This is episode 11, K-nearest neighbors, the simplest model in this entire series.
By the end, you'll tune that one number yourself live on camera.
Every model this series has covered spends time fitting something before it predicts. Logistic regression fits weights. Trees fit splits. SVM fits a margin.
KNN skips all of that. There's no fitting step, literally none.
It just stores the training data and waits. That's the entire .fit call.
This is called lazy learning, and it's the technical term, not an insult.
Here's the whole algorithm start to finish.
A new point shows up. KNN measures its distance to every stored point.
Defines the K closest ones. That's where the name comes from. Those K neighbors vote. Majority class wins. That's the prediction.
No training, no equations to solve, just distance and a vote.
Closest has to mean something specific. That's what a distance metric defines. Euclidean distance. Straight line distance, the default, and the most common choice. Manhattan distance. Adds up movement along each axis, like city blocks.
Minkowski distance generalizes both. One formula, a parameter picks which one you get.
Different metrics can genuinely change which points count as nearest. K is the only real decision you make with this model, and it matters enormously. K equals 1. The prediction copies whichever single point happens to be closest.
That's noisy. One mislabeled neighbor and your prediction flips completely.
A large K smooths things out, but push it too far and it blurs real boundaries away. Somewhere in between is a sweet spot, and it's different for every dataset. Watch what happens to the same data as K changes.
Small k. A jagged, twitchy boundary that reacts to every single point. Classic overfitting.
Large K. A smooth, almost lazy boundary that ignores local detail. Underfitting. This is the bias variance trade-off, compressed into one adjustable number.
Most of the tuning work in KNN is just finding where that boundary settles.
KNN runs entirely on distance, which means scale silently controls everything. Picture one feature ranging 0 to 1, and another ranging 0 to 100,000.
The huge range feature dominates every distance calculation. The other one barely counts.
Scale every feature first, standard scalar or min-max scalar, before anything else.
Skip this step and KNN quietly makes decisions based on units, not on signal.
One more thing worth knowing. KNN struggles as dimensions pile up. In very high dimensions, distances between points start to look nearly identical. Nearest stops meaning much when everything is roughly the same distance away.
This is the curse of dimensionality, a problem worth a full episode later.
In scikit-learn, this is K-neighbors classifier.
Import it. Set n_neighbors to K. Call .fit, which really just stores the data.
Call .predict, and it measures, sorts, and votes behind the scenes. Same three-line pattern as every model this series, this one just skips the math.
Scale your features first, though. Always.
Same dataset, K swept from 1 all the way to 25, scored with cross-validation.
At K equals 1. Accuracy sits around 72%, noisy, overreacting to outliers.
Accuracy climbs as K increases, and peaks around K equals 9, near 94%.
Push K too high, past 20, and accuracy starts sliding back down again.
One number swept across a range, and the right value made a real, measurable difference. KNN shines on small to medium datasets with clean, meaningful distances.
The simple has almost no assumptions, and it's a great baseline to try first.
It's slow at prediction time. Every prediction scans the whole training set. And it needs scaled features or the whole distance calculation falls apart.
For quick baselines and genuinely local patterns, it's still worth reaching for.
Let's lock in what we covered.
Lazy learning, no training phase, just stored data waiting to be compared.
The algorithm, find the K nearest points, let them vote. Distance metrics, Euclidean, Manhattan, Minkowski, and why the choice matters.
Choosing K, the single number controlling overfitting versus underfitting.
Feature scaling mandatory since distance is the entire model.
If lazy learning just clicked for you, subscribe. Naive Bayes is next.
Quick look at where we are in the series. We've now covered trees, forests, SVM, and the distance-based world of KNN.
Episode 12 is Naive Bayes, the math behind spam filters made simple.
It brings probability back into the picture with one surprisingly strong assumption. Episode 12, Naive Bayes explained. No distances, no votes, just Bayes' theorem, and one bold independence assumption.
It's the algorithm quietly running behind most spam filters. Subscribe to catch it. Your challenge task for this episode.
Load any labeled classification dataset. A small scikit-learn toy dataset works great. Task 1. Fit K-neighbors classifier for K equals 1 through 25 and cross-validate each one. Task 2. Plot accuracy versus K. Find where it peaks.
Bonus. Repeat it with standard scalar applied first. Did the best K change?
Try it yourself first. The full solution is in the repo.
Post your best K and best accuracy in the comments.
Zero training. Just distance and a vote. And it still works.
One number, K, was the entire tuning problem.
Episode 12, Naive Bayes Explained, drops next. Subscribe. Comment with the best K and accuracy you found.
I'm Majas. This is CodeToAGI. Let's build.